Imagine sending a message in a bottle, not across an ocean, but across the vast emptiness of space. In 1977, humanity did just that. We launched Voyager 2, a spacecraft no bigger than a small car, on a journey into the unknown. It carried not only instruments but also a golden record, etched with the sounds of Earth, a greeting to any intelligence that might find it. Voyager 2's mission was bold. It would visit the outer planets, gathering data no one had ever seen before. Each byte of information was like a note tucked inside that cosmic bottle, drifting farther from home with every passing day. For decades, those messages came back to us, changing how we see our solar system and our place in it. Today, Voyager 2 is more than 20 billion kilometers from Earth, still whispering its findings across the stars. Its journey is not just a triumph of engineering, it is a testament to human curiosity. The story of Voyager 2 is the story of our desire to know what lies beyond. As we reflect on its legacy, one encounter stands out. Voyager 2's flyby of Uranus in 1986. That moment, and the mysteries it uncovered, would challenge scientists for decades. Voyager 2 was designed for endurance and exploration. Built by NASA's Jet Propulsion Laboratory, the spacecraft weighed about 825 kilograms at launch. Its suite of instruments included cameras, spectrometers, magnetometers, and plasma detectors. Each device had a clear purpose: to observe, measure, and transmit data back to Earth. The mission took advantage of a rare planetary alignment. This alignment, occurring only once every 176 years, allowed Voyager 2 to visit 4 giant planets: Jupiter, Saturn, Uranus, and Neptune, using gravity assists. Each flyby would slingshot the probe onward, conserving fuel and extending its reach. By the time Voyager 2 reached Uranus, it had already rewritten textbooks. At Jupiter, it revealed volcanic activity on Io. At Saturn, it mapped intricate rings and found new moons. Each encounter added to a growing portrait of the solar system's diversity. Voyager 2's technical achievements were matched by its reliability. Decades after launch, it continued to function, powered by radioisotope thermoelectric generators. Its extended mission, now called the Voyager Interstellar Mission, has made it one of the longest operating spacecraft in history. On January 24, 1986, Voyager 2 made its closest approach to Uranus. The spacecraft swept within 81,500 kilometers of the planet's cloud tops. This was the first, and so far, only time a spacecraft had visited Uranus up close. The world watched as data streamed back to Earth. Voyager 2's cameras captured images of a pale blue-green orb shrouded in a haze of methane gas. Scientists hoped for surprises, and Voyager 2 delivered. It discovered 10 new moons, doubling the known satellite count. It also found 2 faint dark rings invisible from Earth. The flyby lasted only a few hours, but its impact was enormous. Voyager 2 mapped Uranus's atmosphere, measured its composition, and took the planet's temperature, a frigid minus 224 degrees Celsius, making Uranus the coldest planet in the solar system. Each reading was a piece of a puzzle, hinting at the strange dynamics of this distant world. The encounter also set the stage for a deeper mystery, a mystery that would puzzle scientists for nearly 40 years. Uranus is unlike any other planet in our solar system. Its most striking feature is its extreme tilt. The planet's axis is tipped at 98 degrees. In other words, Uranus essentially rolls around the sun on its side. This tilt gives rise to bizarre seasons, each lasting about 21 Earth years. As Voyager 2 approached, Uranus's south pole pointed almost directly at the sun. For decades, one hemisphere would bask in sunlight while the other lay in darkness. The planet's atmosphere appeared calm, with few visible cloud features. But Voyager 2's instruments detected subtle bands and storms lurking beneath the haze. The probe also found that Uranus's rings were narrow and dark, made of large, icy particles. The 10 new moons ranged from small, irregular rocks to larger, icy bodies with mysterious surfaces. These discoveries reshaped our understanding of Uranus, revealing a system as complex as any in the solar system. Yet, amid these surprises, one finding stood out: the planet's magnetic field. Unlike any other planet, Uranus's magnetic field was wildly tilted and strangely offset from its center. This enigma would become one of the solar system's greatest puzzles. Voyager 2's magnetometer detected something extraordinary. Uranus's magnetic field was tilted 59 degrees from the planet's rotational axis, and offset from the planet's center by about 1/3 of its radius. Now, most planets have magnetic fields that are, pretty much aligned with their rotation, and these are usually generated by churning metallic cores. But Uranus, well, it totally defied this pattern. The magnetic field there created a lopsided magnetosphere, a teardrop-shaped bubble that trapped solar wind particles in really unexpected ways. As Voyager 2 flew past, it measured wild swings in the field's strength and direction. The data showed that the field lines looped and twisted, forming a complex asymmetric structure. Scientists were honestly baffled. How could a planet's magnetic field be so misaligned? Was it generated by a different mechanism altogether? Some theorized a thin shell of conducting fluid rather than a central core might be responsible. Others speculated about past collisions or even exotic interior chemistry. The mystery only deepened as computer models just couldn't reproduce Voyager 2's observations. For decades, Uranus's magnetic field remained an unsolved riddle, a cosmic message still waiting to be decoded. For almost 40 years, scientists pored over the Voyager 2 data. Despite advances in planetary science, no theory fully explained Uranus's magnetic weirdness. The field's tilt and offset challenged standard models of planetary dynamos. Researchers revisited the data many times, armed with new computer simulations and a better understanding of planetary interiors. Some suggested that Uranus's unique tilt resulted from a massive collision early in its history. Others explored the effects of different materials and temperatures inside the planet. Yet, the magnetic field's strange behavior during the Voyager 2 flyby remained a sticking point. The magnetosphere seemed to pulse and shift in ways that standard physics just could not predict. Each new analysis raised more questions than answers. This scientific stalemate became a lesson in humility. Sometimes the universe resists easy explanations. But Voyager 2's legacy was not just the data it returned, but the curiosity it inspired, a drive to keep searching for truth no matter how long it takes. In 2024, a team of planetary scientists made a breakthrough. Using advanced simulations and newly archived solar wind data, they found that a rare, intense solar storm struck Uranus just days before Voyager 2's flyby. The storm's charged particles collided with Uranus's magnetosphere, distorting its shape and strength. The team compared Voyager 2's measurements with models of how magnetic fields respond to solar storms. The match was striking. The strange tilts and offsets seen in 1986 were not typical of Uranus's magnetosphere, they were the result of a solar event, caught by chance. This discovery did not erase Uranus's inherent oddities, but it explained the bizarre data Voyager 2 recorded. The planet's magnetic field is still unusual, but the most extreme features were temporary, triggered by solar weather at just the right moment. The solution was a triumph of patience and data stewardship. By combining old spacecraft data with new solar observations, scientists finally cracked the Uranus Enigma, a puzzle hidden in plain sight for decades. Voyager 2's journey to Uranus teaches us vital lessons about science. First, timing matters. Had Voyager 2 arrived at a different moment, it might have seen a quieter, more stable magnetosphere. Instead, it captured a rare event, a snapshot of cosmic weather in action. Second, patience and persistence are essential. The answer to Uranus's magnetic mystery took nearly 40 years to find. Science is not always fast. Sometimes progress comes from re-examining old data with new tools and fresh eyes. Third, Voyager 2 reminds us of the interconnectedness of the solar system. A solar storm born on the sun traveled billions of kilometers to change what we saw at Uranus. Every planet, every event is part of a larger cosmic web. Finally, the mission showcases the value of data stewardship. The careful preservation of Voyager 2's measurements allowed future generations to solve mysteries the original team could only imagine. Today, Voyager 2 sails beyond the edge of the solar system, still sending faint signals home. Its encounter with Uranus remains one of the greatest achievements of planetary science. The mission expanded our knowledge, challenged our theories, and proved the value of curiosity-driven exploration. The Uranus Enigma, cracked at last, shows how science moves forward. Each discovery raises new questions. What other secrets do the outer planets hold? What mysteries will future missions reveal, armed with better instruments and deeper insights? As we look ahead, we stand on the shoulders of Voyager 2's legacy. The spacecraft's message in a bottle reminds us, the universe is vast. Our understanding is always growing, and the next great discovery may be waiting in data we already possess. What new enigmas will we uncover as we continue to explore? And who will be there to decipher the next cosmic message in a bottle?